Usually when we talk about human biology, there is this expectation of precision.
Oh, definitely.
Like you look at the vascular system, and it's really tempting to think of it as just a simple set of plumbing. You've got pipes, you've got a pump, and, fluid moves around.
Right, it's a comfortable analogy. A bit mechanical, maybe, but it makes sense on a macro level.
Then you look closer, like you take a literal drop of blood, and suddenly that simple plumbing analogy it completely falls apart.
Yeah, it really does.
We're looking at a microscopic landscape that is honestly a highly regulated, impossibly intricate superhighway, and we take it entirely for granted every single second we're alive.
It is the absolute definition of a biological marvel. And, we aren't just going to look at what blood cells do today, but really why their specific microscopic design is an evolutionary triumph. We need to look at the engineering behind the fluid.
Okay, so let's unpack this. Welcome to this deep dive. For you, the learner listening right now, your mission today is to uncover the brilliant, hidden engineering inside your own bloodstream.
Exactly.
We're pulling from an incredibly detailed medical text on human physiology. Specifically, Chapter 33, focusing on red blood cells, how they operate, and what happens when the system breaks down into conditions like anemia or polycythemia.
Right, we're going to explore how the body creates, regulates, and sometimes really struggles to maintain that perfect balance of oxygen delivery.
And before we can understand how this biological factory operates, we really have to look at the incredibly specific design of the product itself, the red blood cell or erythrocyte.
Right.
Most of us know the basic job description, right? It transports hemoglobin, which carries oxygen from your lungs to your tissues. But I was surprised to learn it does so much more than just ferry oxygen around. It also houses something called carbonic anhydrase.
Yeah, and that is a crucial enzyme. You have to remember, your cells are constantly producing carbon dioxide as exhaust.
Like a car engine.
Exactly. And if that CO2 just dissolved into your blood water like a soda, your blood would become dangerously acidic. And, well, it would move far too slowly to be exhaled in time. Carbonic anhydrase actually catalyzes the reversible reaction between carbon dioxide and water to form carbonic acid.
And it does this quickly, right?
Oh, incredibly fast. It speeds up this reaction several thousand times.
Thousands of times. So it's essentially a chemical supercharger.
It really is. This extreme rapidity makes it possible for the water in your blood to transport massive, almost unbelievable quantities of CO2 in the form of bicarbonate from the tissues back to the lungs.
Wow.
And on top of that, the hemoglobin inside these cells acts as an excellent acid-base buffer. So the red blood cell isn't just an oxygen truck, it's basically responsible for keeping the pH of your entire bloodstream stable.
And they do all of this heavy lifting while being unimaginably tiny. I mean, they look like little biconcave discs, like a donut without the hole punched all the way through.
They do, yeah. They have a mean diameter of about 7.8 micrometers. And just to give you a sense of scale, there are millions of them in a single microscopic drop.
Millions.
Yeah, in healthy adult men, the average is around 5.2 million per cubic millimeter. In women, it's closer to 4.7 million.
Wait, why the discrepancy between men and women? Is that just like a body size thing?
Not exactly. It actually comes down to hormones. Testosterone stimulates the production of erythropoietin, the hormone that triggers red blood cell creation, much more strongly than estrogen does.
Oh, interesting.
Plus, women naturally lose blood during menstruation, which keeps the baseline count slightly lower. But regardless of gender, I mean, the sheer volume is staggering. And their distinctive biconcave shape is not an accident.
No, it's brilliant. I like to think of the red blood cell as a squishy, highly deformable water balloon. The biconcave shape means it actually has a great excess of cell membrane for the quantity of material inside it.
Which is key for travel.
Right. So as it travels through your body, it can squeeze into incredibly tight capillary spaces narrower than the cell itself, and deform into almost any shape without stretching the membrane enough to pop.
What's fascinating here is why the hemoglobin must be kept inside this specific balloon in the first place. I mean, you might wonder, why not just let hemoglobin float freely in the blood plasma?
Yeah, if it's just a protein that binds to oxygen, why cage it inside a cell at all? Some invertebrates actually do that, right? Just free-floating oxygen carriers.
They do, but human blood pressure and kidney filtration make that impossible for us. If human hemoglobin were free-floating in the plasma, about 3% of it would leak through the capillary walls into the tissue spaces.
Oh, wow.
Or get shoved right through the kidney's microscopic filtering system, the glomerular filtrate, every single time the blood passes through.
Wait, So you'd just be constantly peeing out your oxygen carrying capacity. You drain your own supply in hours.
Precisely. The red blood cell is essentially a necessary containment suit to prevent massive, constant leakage of your most vital respiratory protein.
That makes perfect sense. But because these fragile little balloons are constantly squeezing through tight, twisting capillary pipes all over the body, they inevitably wear out. They take a beating. So where do they come from? Like, how does the body replace them?
Well, the location of your body's blood factory actually shifts dramatically over your lifetime. It's not a static process at all.
This blew my mind. In the early weeks of an embryo's life, red blood cells are produced in the yolk sac. Then, during the middle trimester of gestation, the liver becomes the main factory, with some help from the spleen and lymph nodes.
Right, and as the skeletal system develops during the last month of gestation and throughout early childhood, the bone marrow takes over entirely. Essentially, all your bones are working overtime, producing red blood cells until you were about 5 years old.
But then the factory just shuts down in half the body. Like after age 20, the marrow of your long bones, like the humerus in your arm or the femur in your leg, just stops making red blood cells. Why do they retire so early?
It's basically a matter of biological real estate and energy conservation. As we reach adulthood, we simply don't need the massive body-wide production capacity that a growing child does.
Makes sense.
So the marrow in those long bones mostly becomes replaced with fatty tissue. From then on, blood production is strictly localized to the membranous bones, the vertebrae in your spine, your sternum, your ribs, and the ilia of your pelvis.
And the actual assembly line inside those specific bones is incredibly complex. All blood cells begin from a single type of cell in the marrow called the multipotential hematopoietic stem cell.
It's a mouthful, but think of it as a blank slate master cell. These multipotential stem cells divide. Some remain as master stem cells just to maintain the supply, but others differentiate into what are called committed stem cells. They've, chosen a career path.
Right.
For red blood cells, this committed stem cell is called a colony-forming unit erythrocyte, or CFUE.
And from there, the actual red blood cell starts to take shape. It goes through several dividing stages, from a proerythroblast down through various erythroblast stages, where it's essentially filling up with hemoglobin.
Yeah.
And as it fills up, it condenses its nucleus until it finally just spits the nucleus right out of the cell.
It literally ejects its own command center to make more room for oxygen.
Here's where it gets really interesting, though. After it spits out the nucleus, the cell enters this stage where it's called a reticulocyte. And, reading the text, I couldn't help but picture a reticulocyte as a teenager cell.
A teenager cell. I like that.
Yeah. It's almost ready to be a functional adult, but it still have a bunch of leftover junk scattered around its room. It contains basophilic material, remnants of the Golgi apparatus, a few mitochondria.
That's a highly accurate way to visualize it. It's functional, but not fully refined yet.
And it literally packs up this junk and takes it on the road. The reticulocyte squeezes through the cellular walls of the bone marrow to enter the bloodstream in a process called diapedesis.
Diapedesis, yes.
I love that word. It just squishes its gelatinous body right through the pores into the blood. It circulates as a teenager like that for a day or two before the remaining internal material finally dissolves, and it officially becomes a mature erythrocyte.
And if we connect this to the bigger picture, it's really vital to realize that this entire factory process inside the bone marrow isn't autonomous. The growth of these cells is driven by external proteins called growth inducers, like interleukin-3.
But those growth inducers just tell the stem cells to multiply, right? They don't tell them what to become.
Correct. That is the job of differentiation inducers. And the formation of both of these inducers is controlled by factors completely outside the bone marrow. The bone marrow factory doesn't blindly produce 1 million cells a minute just because it can. It waits for very specific external work orders based on the body's environmental needs.
Which perfectly sets up the next huge piece of the puzzle, the body's oxygen thermostat. If the bone marrow is the factory, how does it know when to speed up production? It turns out your body doesn't actually count the number of red blood cells floating around. It measures the oxygen they deliver.
Exactly. Tissue oxygenation is the ultimate non-negotiable regulator. If you have conditions that decrease the quantity of oxygen transported to your tissues, say an extreme hemorrhage where you've lost blood, or you just move to a very high altitude where the air is thin, your body immediately senses that cellular hypoxia.
And that low oxygen state triggers a chemical chain reaction. The hypoxia leads to increased tissue levels of a protein called HIF1, or hypoxia-inducible factor 1. And HI1 essentially acts as an emergency beacon. It binds to the DNA and activates the erythropoietin gene.
Erythropoietin, commonly known as EPO, it's a circulating hormone. And when EPO hits the bloodstream, it rushes to the bone marrow and violently stimulates the production of proerythroblasts from those stem cells.
It kicks the factory into overdrive.
It really does. It also speeds up their passage through all those teenage erythroblastic stages we just talked about.
But the timing of this is what caught my attention. If you're placed in a low-oxygen environment, EPO starts forming within minutes. It hits maximum production within 24 hours. But almost no new red blood cells actually appear in your blood until about 5 days later.
Right, there's a delay.
There's a 5-day lag on the work order, which made me wonder, if I'm bleeding out today and my body takes 5 days to manufacture replacement cells, how do I survive the week?
It's a great question, and it really comes down to differentiating between blood volume and blood composition. If you suffer a severe hemorrhage, your body will rapidly pull water and fluids from your tissues into your blood vessels to restore the physical volume.
Oh, just to keep the pressure up.
Exactly. It needs that fluid pressure just to keep your heart pumping. That happens in hours. But the fluid replacing the lost blood doesn't have any oxygen carrying capacity, so you survive the immediate pressure drop, but you remain severely anemic and weak until the bone marrow catches up 5 days later with the actual red blood cells.
Biology takes time to assemble the product, and where that EPO comes from is critical to this whole system. Normally, about 90% of all erythropoietin is formed in the kidneys. Only 10% is formed in the liver.
Which means the kidneys aren't just filtering waste, they're the primary atmospheric sensors for your entire circulatory system.
So what does this all mean? If 90% of this critical hormone comes from the kidneys, what happens if your kidneys fail? If someone's kidneys are destroyed by renal disease, severe anemia is the unavoidable consequence.
Unfortunately, yes.
Because that backup 10% from the liver is only enough to cause maybe a third of the red blood cell formation the body actually needs to function. It really highlights how interconnected these systems are. I mean, you wouldn't immediately link kidney health to being out of breath, but they are absolutely tethered together.
This raises an important question, though, regarding non-renal sensors. At times, hypoxia in other parts of the body, completely outside the kidneys, can still stimulate kidney erythropoietin secretion.
Oh, really?
Yeah, this suggests there are non-renal sensors sounding the alarm and sending chemical messengers to the kidneys. Specifically, hormones like norepinephrine, epinephrine, and several prostaglandins can also independently stimulate EPO production.
I love that the body has redundant backup alarms. But, even if the kidneys send a massive EPO work order, the bone marrow factory can't build these red blood cell water balloons out of thin air. It needs the right raw materials. And that brings us to the supply chain: iron, vitamin B12, and folic acid.
Let's start with iron, which is the absolute heart of hemoglobin formation. And instead of just looking at the chemistry as a list of ingredients, you really have to look at it as a microscopic forge. Iron is highly reactive. If it's just loose in the body, it's toxic. It generates free radicals that destroy tissue. So the body has to build a highly specialized cage for it.
Right. The cell takes raw materials, succinyl-CoA and glycine, and carefully constructs a multi-layered molecular cage called a porphyrin ring.
Exactly. 4 of these rings lock together, and right in the center, they trap a single atom of iron. This newly formed structure is called heme. The cage keeps the iron safe, but leaves it just exposed enough to temporarily bind to an oxygen molecule.
Then the cell binds 4 of these heme cages together with long protein chains to form one complete hemoglobin molecule. It's microscopic precision manufacturing, but getting the iron to the factory is a whole other logistical nightmare.
Oh, absolutely.
An average person has about 4 to 5 grams of iron total in their body. The way we absorb it from food is a slow, highly guarded process. When iron is absorbed from the small intestine, it immediately gets picked up in the blood plasma by a carrier protein to form something called transferrin.
Transferrin is the transport vehicle. Excess iron is dropped off in the liver, where it's stored as ferritin. But what's truly remarkable about transferrin is how it interacts with the bone marrow. It doesn't just drop the iron off at the loading dock. The transferrin binds strongly with specific receptors directly on the cell membranes of the erythroblasts.
And the cell literally swallows the whole package.
It does.
Through a process called endocytosis, the erythroblast engulfs the transferrin, pulling the iron directly inside, straight to the mitochondria, where that porphyrin cage is being synthesized. Talk about a secure, direct-to-door delivery service.
It is highly efficient, and it has to be because iron is so volatile. But iron isn't the only critical material. The physical maturation and division of these cells rely heavily on vitamin B12 and folic acid. Both are absolute prerequisites for the synthesis of DNA.
Right. Without B12 or folic acid, the cells can't form thymidine triphosphate, which is an essential building block of DNA. So the DNA ends up abnormal. The bone marrow tries to produce red blood cells, but
They fail to mature and divide properly.
yeah,
You end up with these massive mutated cells called macrocytes. They are flimsy, oval-shaped instead of tight biconcave discs. And while they can technically carry oxygen, their membranes are so fragile they have a fraction of the normal lifespan.
which brings us to a devastating condition called pernicious anemia. It's a maturation failure caused by poor absorption of vitamin B12. But the root cause isn't necessarily a lack of B12 in your diet, right?
Usually not, no.
It's often caused by an autoimmune issue, where your stomach lining, the gastric mucosa, atrophies and fails to produce something called intrinsic factor. This was my favorite mechanism in the entire text. I couldn't help but picture intrinsic factor as an armored escort. If you just eat a steak rich in B12, that vitamin would be completely obliterated by your harsh gastrointestinal digestive enzymes before it could be absorbed.
It wouldn't survive the journey.
Exactly. So the stomach secretes this intrinsic factor, which binds tightly to the B12. It wraps it up, acting like an armored vehicle, protecting the B12 from digestion as it travels all the way down into the small intestine.
And I assume the escort helps it get inside the bloodstream, too.
It does. Once it reaches the ileum, the intrinsic factor binds to specific receptors on the intestinal walls. Then, through a process called pinocytosis, which is essentially the cell folding its membrane inward to drink the surrounding fluid, the armored escort and the B12 are pulled into the blood together. Without that specific escort from the stomach, the B12 never makes it inside, no matter how much you eat. And the timescale of this is what's truly mind-blowing to me. Let's say your stomach stops producing intrinsic factor today. You won't actually become anemic tomorrow.
Not even close. Once absorbed, B12 is stored in massive quantities in the liver. The minimum amount you require daily is incredibly tiny, only 1 to 3 micrograms, but your liver stores about 1,000 times that amount.
That's incredible.
Because of this massive reserve, it takes 3 to 4 years of defective absorption before a person finally burns through their stockpile and begins showing symptoms of pernicious anemia.
3 to 4 years running purely on biological reserves. Unbelievable. Now, if the system works, if we have the iron, the B12, the perfect biconcave shape, we have these brilliant little water balloons zooming around delivering oxygen. But even the best engineered products have an expiration date.
They do. The lifespan of a normal red blood cell is strictly capped at about 120 days. Even though they lack a nucleus and mitochondria, they do have cytoplasmic enzymes that metabolize glucose just to keep the cell membrane pliable and prevent their internal proteins from oxidizing. But eventually, the metabolic machinery wears down. The cell membrane becomes incredibly fragile.
And when they become fragile, the body doesn't just let them pop randomly in your brain or your heart. It forces them through a filtration system. The spleen acts as the ultimate gauntlet. The spleen is packed with trabeculae, essentially a tight internal scaffolding or meshwork. The spaces between this mesh are only 3 micrometers wide. But remember, the red blood cell is 8 micrometers in diameter.
So young, pliable cells just squish right through the scaffolding without an issue. But these old, fragile cells attempt to squeeze through, and their weakened membranes finally just rupture under the mechanical stress.
It's a purposeful demolition. And when they rupture, local immune cells called macrophages immediately swarm the debris and eat the loose hemoglobin. Over the next few days, these macrophages release the iron back into the blood to be carried by transferrin back to the bone marrow, to be recycled into new cells. Meanwhile, the crushed porphyrin cage is converted into bilirubin, which goes to the liver and gets excreted in bile.
It's the ultimate biological recycling program. Nothing goes to waste. But we have to look at what happens when there's a permanent deficit. We talked about pernicious anemia, but there are several other profound glitches in this system, for instance, blood loss anemia. If a person has a chronic slow bleed, say, from an undiagnosed ulcer, they can't absorb enough iron from their diet to keep up with the continuous loss.
So the bone marrow has to build cells with less iron. The result is microcytic hypochromic anemia. The cells are physically too small and look incredibly pale because they have so little hemoglobin inside them.
There is also a plastic anemia, where the bone marrow factory itself is destroyed or non-functioning. This is often the result of high-dose radiation, chemotherapy, or exposure to toxic chemicals that wipe out the stem cells. And then there are hemolytic anemias, where the factory is fine, the cells are perfectly formed in number, but they have structural defects, making them incredibly fragile.
Right, like hereditary spherocytosis, where a genetic glitch makes the cells spherical instead of biconcave. Because they're rigid spheres, they can't withstand compression at all, and they immediately burst the second they hit the spleen's gauntlet. And then, of course, there's sickle cell anemia, which is a genetic defect in the actual molecular chain of the hemoglobin itself.
Yes. In sickle cell anemia, a single amino acid valine is accidentally substituted for glutamic acid in the beta chains of the hemoglobin. When this abnormal hemoglobin is exposed to low oxygen environments in the tissues, it physically precipitates into long, rigid crystals inside the red blood cell.
And those rigid crystals elongate the cell into a sharp sickle shape. Instead of a squishy water balloon, you suddenly have a rigid shard that gets stuck in the capillaries, rupturing itself and blocking blood flow. It's a devastating mechanical failure. And all of these anemias have profound secondary effects on the circulatory system as a whole. This is a mechanism I'd never fully considered: the actual viscosity or thickness of the blood.
It's a vital physics concept here. Normal blood is about 3 times as viscous as water. But in severe anemia, where you lack red blood cells, your blood dramatically thins out. The viscosity can fall to just 1.5 times that of water.
Which means it flows too easily. It significantly decreases the resistance to blood flow in your peripheral blood vessels. And because your tissues are starving for oxygen, your blood vessels dilate to try and get more flow. The return of this thin, fast-moving blood back to the heart skyrockets. This forces the heart to dramatically increase its cardiac output, sometimes pumping 3 or 4 times the normal volume of blood just to keep the tissues alive.
Exactly. The heart is running a marathon just while the person is sitting still, which sort of masks the lack of oxygen while they're resting.
But if a person with severe anemia actually stands up and starts to exercise, their heart is already pumping at absolute maximum capacity just to maintain baseline. It literally cannot increase flow any further. This leads to extreme tissue hypoxia. It can cause acute cardiac failure on the spot.
Now, on the completely opposite end of the spectrum is a condition called polycythemia, having far too many red blood cells. There is secondary polycythemia, which is just an automatic physiological response to low oxygen. If you move to 17,000 feet, your red blood cell count will naturally rise from 5 million to 6 or 7 million per cubic millimeter just to capture the thin air.
But then there's a pathological condition called polycythemia vera. It's a genetic aberration in the bone marrow stem cells. They basically act like a tumor, completely ignoring the EPO thermostat and refusing to stop production. The hematocrit is the total percentage of your blood that is comprised of red blood cells can jump from a normal 40% all the way up to 70%. And the viscosity of the blood increases to 10 times that of water.
10 times?
Wait, if the viscosity is 10 times that of water, the blood is essentially turning into thick sludge. How does the heart even pump a sludge like that through the microscopic capillaries? Wouldn't the resistance just stop the heart entirely?
You'd think so, but it creates a fascinating physiological paradox. You are absolutely correct that the extreme viscosity heavily decreases the rate of venous return to the heart because the sludge moves so slowly through the pipes. However, in polycythemia vera, the massive total volume of the blood is vastly increased. The sheer physical pressure of all that extra fluid pushes hard against the vessels, which tends to increase venous return.
That is wild. The sluggishness slows it down, but the heavy pressure pushes it forward.
Precisely. These two opposing factors basically neutralize each other, keeping the cardiac output surprisingly close to normal. But it's not without severe consequences. Because the thick blood flows so sluggishly through the skin's capillaries, a much larger than normal quantity of the hemoglobin gets deoxygenated by the surrounding tissues before it even enters the venous system.
And deoxygenated blood is dark. So the blue color of all this spent hemoglobin heavily masks the red color, giving the patient a ruddy, bluish, or cyanotic tint to their skin. The system survives, but it is heavily strained.
Incredible. So we've traced the entire journey today. We started with the perfect biconcave water balloon design of the red blood cell. We saw how its birth in the bone marrow is strictly dictated by a cellular thermostat in the kidneys measuring oxygen. We followed its highly guarded iron supply chain, requiring cellular swallowing and armored escorts for vitamins. And we looked at its eventual, highly managed demolition in the microscopic gauntlets of the spleen, unless structural glitches throw the whole system into life-threatening chaos.
It is a phenomenal, tightly wound system, and I want to leave you, the listener, with one final, almost philosophical paradox from this chapter to ponder as you go about your day.
Let's hear it.
Red blood cells exist solely to transport the oxygen that powers the entire human body's metabolism. Without them, we die in minutes. Yet to make room for maximum payload, to ensure they can carry every last possible molecule of oxygen, mature red blood cells permanently jettison their own mitochondria, the very organelles required to process oxygen for energy.
They carry the ultimate fuel for the entire body, but they are entirely incapable of using it themselves.
Exactly. They rely entirely on basic low-yield glucose metabolism just to survive their 120-day journey. They carry the very thing everyone else needs to thrive, but cannot touch a single drop of it themselves. Next time you think of the circulatory system as just plumbing, remember that microscopic superhighway. Remember the hidden selfless engineering in every single drop. Thank you for coming on this deep dive with us.